and I'm going to let you go at it. So why don't you make a great presentation? It's all yours.
Okay, let me get the thing up. Oh, wait.
And in fact, I'm going to mute myself because I'm not presenting.
Hold on, is it? Okay. Hold on, where? It's just hard to use freaking Google Slides. I gotta figure out where the heck I put the. There it is. There we go. Okay, so we did our presentation on machine learning. Now, before we can learn what machine learning is, first we have to get into what an algorithm is. Basically, an algorithm is a set of rules to be followed in calculations by a computer. It's got to have 5 characteristics. It's got to have an input. It's got to have an output. It has to be definite. It has to work, and it must be finite. Now, 2 examples of algorithms that you've used before is a recipe and long division. Machine learning is a form of I can't speak today. Machine learning is a concept where machine learning is a form of artificial intelligence, and it excels at finding patterns. Basically, the idea behind it is that an algorithm improves over time through experience and the collection of data. And if you feed more data you feed it, the more it improves. Although it apparently takes a very long time for it to improve. It's best when, and it should involve as little human intervention as possible. Now, machine learning has a bunch of different applications. Speech recognition software uses it to help understand what you're saying better. Banks use it to see how likely you are to not pay them back. Uh, Stockbrokers use it to see how the stock market to predict how the stock market will behave. Companies use algorithms to sort through all that that data that they gather to sell you stuff. That makes search engines more efficient. There's a reason why there's a reason why whenever you Google something, if you look closely at the top, it says whoever results in fractions of a second. Because they're pretty proud of that algorithm, I guess, because that's a lot of data to sort through. It also improves GPS directions, traffic alerts, and doctors use it to help diagnose and treat patients faster. Now, here's a very simple example of an algorithm. It's Euclid's algorithm for the GCD of 2 numbers. We know it's an algorithm because it's got an input, it has an output, it's finite, it's well-defined, and it works. Here we have a bare bones example of a algorithm a doctor would use to, I can't speak today, a doctor would use to diagnose a patient. Now, this one, I can't really show you any of the calculations of the actual algorithm because, well, companies don't really like showing people that stuff because they're proprietary technologies. Okay, and basically, you type in the symptom, you type in the symptoms, you put in any environmental, genetic factors, any physiological data you've got. It assesses it. It tells you what treatments to do, and if it can't figure it out, it keeps doing more tests until you finally diagnose it. Here's a much more complicated one that a optometrist would use to diagnose what's causing your vision loss. The thing about algorithms and machine and about algorithms that they get better over time. So basically, the more you use this, the more criteria it has to narrow it down, the better it should get. Okay, that's my section.
Okay, so computers don't have the same intuition as humans do. So you can't just tell a computer to solve a system of equations by substitution. So we have to deal with it in a more systematic approach to it. And that's why we use linear algebra. Not to mention that these data sets have millions of variables, so you don't really want to be doing it through substitution. For a computer to be able to deal with such quantities, you have to approach it algorithmically, and that's where linear algebra helps because the matrix and matrix operations are really the basis of machine learning, together with multivariable calculus. The real connection is like when you manipulate matrices in a way that makes the calculations far easier, so that a computer doesn't take forever to calculate whatever you're trying to calculate. And that goes into complexity theory. And if you want to read more on that, you can. Some methods to know are eigen decomposition and singular value decomposition. Eigen decomposition is just allowed when a matrix is diagonalizable, and singular value decomposition is more generally applied, and it works whenever two vector spaces that you're looking at have an inner product. Next slide. So when you're presented, this is for eigen decomposition. When you're presented with a data set of matrix A, you can decompose it by diagonalizing it, which is finding its eigenvalues and eigenvectors. And this is basically the equation. Next slide. It's that top A equals Q lambda, and that's capital lambda, and Q inverse, which is basically our diagonalizing of A. Next slide. So this is basically a representation of what's happening. As you can see, you start out with the parent matrix A, and that's equal to the eigenvectors times the diagonalized eigenvalues times the inverse of the eigenvectors of A. Next slide.
Okay, there we go.
Yeah. So basically, this is for singular value decomposition. This is more generally applied, and it's applicable when two vector spaces have an inner product. It doesn't result in the compression of a matrix, so you don't lose any data. And it's useful because you can find a pseudo inverse, and a pseudo inverse is a inverse of a rectangular matrix, so non-square. So that's really useful. Next slide. The pseudo inverse is denoted as D superscript plus, and the equation is A transpose times the inverse of A times A transpose. And you can use that to typically just directly solve for the equation AX equals B for X, solving for X. Next slide. This is basically the process by which you find singular values. You start with your data set M, and it doesn't need to be a square matrix. It's typically rectangular. But when you multiply it times its transpose, you get a symmetric and square matrix, which is what we need. The next step is finding the eigenvalues and eigenvectors and normalizing the eigenvectors. Next slide. This results in our orthonormal input basis O, which is just the set of all the vectors, eigenvectors. These values are known as singular values, the right singular values. And we use these to find the eigenvectors for M transpose, which is the bigger of the two matrices. They're both square. And you can see it's M times U times M times U n minus 1, because the last one we find through the eigenvalue equaling 0. By dividing by their lengths, you get an orthonormal output basis O. I'm not sure what to call that symbol, but O dash. These values are the orthonormal input basis, and they're known as left singular vectors of matrix M. And this is all you need to get your new matrix for the linear transformation. It's equal to Q inverse times our original matrix times P, where P and Q are our change of bases matrices, respectively to the column vectors O and O dash. Next slide. So there's a really nice geometric interpretation of this. You can basically think of it as providing an orthonormal basis by which a linear transformation can change, can stretch, the input basis. Next slide. This is a graphical representation. You can see the first one. You have your basis and your axes. And once you apply the linear transformation, you can see the bases has stretched into dimension of 3 by, you can see the z-axis has been added. So basically you're just stretching out our original matrix into a different basis. Next slide. Linear regression. These are two of the main techniques of finding like data. Linear regression is the relationship between one or more input variables. If there's more than one, it's called multivariate, and a single dependent variable. And the goal is to minimize the error in the prediction of whatever you're trying to predict. The method typically used to find the error is called least squares. And you can see it's E equals B minus AX. And when E equals 0, it's known as an exact solution to AX equals B. Our goal is to minimize E so that, and that's what our least square solution would be. As you can see, those dots, they're the errors. And we're typically trying to get those dots as close to the line as possible. And that's how we minimize the error. Next slide. The second technique I'm touching on is principal component analysis, PCA. And it's a method to reduce dimensionality of a set of given data. And that's just, you can typically think of it as projecting M columns into a subspace of M or fewer columns without changing the data too much. Next slide. This is typically the process. So if you're given a set of data in matrix form, A, you obtain the mean values of A, the columns of A, and you subtract that from every value of A and divide by the standard deviation. This is referred to as standardization. Next, we obtain the covariance matrix, which is a P by P symmetric matrix where the entries are the covariances associated with all possible pairs of initial variables. And we set that as our matrix V. Next slide. You then decompose V using singular value decomposition or eigen decomposition. And this provides a new basis for the new subspace of A. Typically you choose M components, the K largest of the eigenvalues, and we call these the principal components. Note that if all eigenvalues are similar, the data is already compressed, and doing this really doesn't do much. And any eigenvalues that are close to 0 don't mean anything, so they can be discarded. And finally, to get our projection into the new subspace, we multiply B transpose times A, our original matrix. Next slide. So basically, this is the process by which you go about. You start with your correlated data. You choose the new basis, and you want the dimension of the highest variance. You compute the covariance matrix, and there's an example right there, a small one, but then you find the eigenvectors and eigenvalues of the covariance matrix, and you choose the eigenvectors with the highest value. And once you do your equation, you project your data into those eigenvectors, and you end up with the last part. Next slide. And this is basically what's happening. You start with your original 3-dimensional space, and once you apply the principal component analysis, you can see that your new axes are the principal components, and so you're changing the basis of the original matrix. Next slide. Next slide.
Jordan, why don't you stop sharing your screen and I'll pick it up from here.
Okay.
Okay. Can everybody see my screen?
Yes.
Okay. I'm going to try to go through this super quickly since I know we're short on time. So just interrupt me if anything is like exceptionally unclear. So neural networks, this is basically just like one version of machine learning that we've talked about, inspired by biological nervous systems. Some of the key points that I'm going to go through with neural networks are the layering of a network, which is basically just the digital architecture, how we train that network and how we use something called a cost function to help train it, and backpropagation through the network, which is a series of calculations and a technique that's used to help fine tune the network. And it's called backpropagation because it works in reverse through the network, but that'll make more sense in a minute. So when we put these words together, what do they actually mean? You can think of this network. This is sort of a simple one that you can just hold in your head for the purposes of this presentation. And imagine all of these little circles as neurons within our network. Here, this first layer is inputs. So these neurons will receive some kind of data from the world. It'll be transmitted through the network. It'll hit a second layer of neurons, which for now, imagine these as functions that receive input data from the previous layer, and they do something with that data and then send it to every single neuron in the next layer. And this is just an iterative process that happens at every layer, basically transmitting our raw data through the network until we reach outputs. And in a digital neural network, each neuron is a function that's basically designed to hold a number. And normally that's a number between 0 and 1. And that's a key difference from biological networks where neurons are either active or inactive. So biological neurons are 0 or 1, binary, where digital neurons are anything in between 0 and 1. So they hold continuous values, which is important, and I'll explain why later. So let's try to just understand how this works by looking at this one neuron Y. And I just called it Y because I made it yellow. So let's look at a couple of things that influence the activation level of this neuron. So what value is it going to take between 0 and 1? For now, let's just imagine there are two categories of things that really influence the activation level of this neuron. And our first category of things is the activation levels of the neurons in the preceding layer. So 1, 2, 3, and 4. And based on this little drawing here, let's imagine number 4 is activated much higher. It's got a brighter color, so it's closer to 1. Just based on the activation level, number 4 will have a stronger influence on Y than number 1. But then the second component of things that influence the activation of neuron Y are the weights, which all this word weights means is the strength of the connections between neurons. So that's what these colored lines are. Each colored line is a weight. So this pink line is the weight between 1 and Y. How strongly are those two neurons connected? So those are the first two categories of parameters that influence the activation of neuron Y. And so how do we describe this with math so that a computer can understand it? It's actually, pretty intuitive considering what we just talked about. We want the activation level of a neuron in the preceding layer times the strength of its connection to neuron Y. And that's exactly what's going on here. We have, for example, neuron 1 to Y, the weight of the connection between neuron 1 and Y, and the activation level of neuron 1. So we just sum all these up and we have our activation of neuron Y. But notice in this formula, there's nothing that's explicitly preventing our activation level of Y from being in between 0 and 1. These values can combine in a way to give us a negative number or a value greater than 1. So there's something else we have to do to bound our activation level of Y. And that's what this sigmoid function is. So we keep everything identical within the parentheses here. It's still our weights times our activation levels of the first neurons. But then we just apply some kind of function outside of the quantity within the parentheses. And from what I read, this function, the sigmoid function, is a little outdated, but it's helpful for trying to understand what's going on. Basically, if the value inside the parentheses turns out to be super negative, the sigmoid function will convert that into a value very close to 0. Where if the value inside the parentheses turns out to a very positive number, the sigmoid function will convert that into a number very close to 1. So the sigmoid function is just bounding the level of activation of neuron Y. Okay, and a third thing we can do is create something like a threshold for our neuron Y. Say we only want it to fire when there's like very strong influence. We only want it to fire when there's very strong data telling it to fire. We introduce this bias term within the parentheses. So for example, imagine it's -10. In order for the activation of neuron Y to register close to 1 on our sigma function, the sum of the weights times the activations of the previous neurons will need to be much greater than 10. So now it doesn't just have to be greater than 0, it has to be greater than 10. So that's sort of like creating a threshold for our neuron Y to fire. Okay, so how do we do this with matrices? Here's just a pretty simple schematic of what's going on. Now we're talking about AN. N just stands for neuron. I could have made it O for orange since it's orange now. But basically, we take what we have here that's representing the activation level of neuron N. And you can imagine that in a larger neural network, we're going to have thousands of equations like this, which are just going to be impossible to sort through and calculate. So we take our equations like this and reorganize them into matrix format. So we've got one matrix here that's holding the weights of the connections that we care about. Another column vector that's dealing with the activation levels of neurons in the preceding layer, and then the biases associated with those particular neurons. And then we have our little sigma bounding function on the outside. So we've basically taken, potentially hundreds or thousands of these equations, and we've compressed them into a single, admittedly still daunting matrix equation, but this is something a computer can handle. And then the output in this column vector is associated with the activation level of the neurons in our next layer. So that's where linear algebra helps here. So let's start talking about how we train a neural network. Imagine we've got some sets of data as inputs, and we want to use these inputs to determine if someone is an arts student or a STEM student. And we think we've got, pretty relevant data on, characteristics that can help our network make this decision. So it's important to know that at first, these networks operate totally at random. There's like no predisposed algorithm within the network. It's just doing calculations at random. So our first output is probably going to look something like this. It's meaningless to us. There's 40% chance this person's an art student, 60% they're a STEM student. We want our network to eventually be giving us something close to this. Like, okay, we're nearly 100% sure this person's a STEM student. And we start to train this network by developing something called a cost function, which if you look at it, it's almost like a regression function, like a least squares. You've just got the difference between the output from your network and what it should have output squared, and you sum all those up. So, for our example here, 0.6 minus 1 squared, 0.4 minus 0 squared equals 0.32. And we want to get this value of the cost function as small as possible, because that means our network is working more accurately. Oh, here, I'll start my video. Okay. So part of the training involves a phenomenon called gradient descent, which in the number of dimensions that neural networks are working at, it's almost, it is impossible to visualize, but we can think of it as something happening on this three-dimensional surface. So imagine the algorithm that our network uses first, its random decision of some network, is this red ball on the surface. And imagine the altitude of the surface represents the value of our cost function. We want that to be as minimum as possible. So the global minimum of this surface is over here. But the technique gradient descent, and people probably remember from multivariable calculus what a gradient is. It's just how you find the steepest part of a surface or a function. Anyway, you just take the negative of that and you go in the opposite direction. So now you're going down the gradient. Basically, it's a series of calculations that help our network start to walk down this surface towards some local minimum of the cost function. And one important thing to notice here is that once you're at the bottom of the local minimum, you've only trained your network to walk downhill. So even if there is a global minimum over here, you're not going to make it there. Your network doesn't know how to walk uphill. So it may not be perfectly optimized, but it's locally optimized. So we'll keep moving. There we go. Okay. And then part of how this cost function works is it takes all of the weights and biases within the network as inputs. So that's why I was saying it's impossible to think of this in the number of dimensions that a network is operating at. But basically, it's taking all of our weights and biases as inputs and giving us some column vector output that might look like this. And once we've got this column vector output, we can look at the magnitudes of the elements within the column vector. And we can say, oh, well, this magnitude of 0.88 is close to 1. What is that magnitude associated with? And we can say, oh, it's associated with this weight here. So that weight, having a larger magnitude in the column vector output, means that it's more influential on changes in the cost function. So adjusting elements in this column vector output with larger magnitudes will be more effective at reducing our cost function and improving the accuracy of the network. So training with backpropagation, this is
Be finishing up pretty soon because the other
yes, yeah, this is basically the last thing. And I'll go super quick. Let's imagine a really easy example here, 2 neurons. Well, I'll just skip through most of it actually. All we're doing here is trying to determine which parameters the cost function is most sensitive to. So this partial differential here is just looking at, okay, how sensitive is the cost function to changes in the weight? And then you do some chain rule calculus and you get an equation like this. So this is basically breaking down how sensitive cost is to weight. And then you do that again with biases right here, the little b, and then activation levels of neurons in the first or in the previous layer. So basically that's just telling us how sensitive the cost function is to certain parameters. And then you can't do that until you've got an output. So that's why you start at the output layer, you see how wrong your network was, and then you work back through until you hit the input layer again. It gets more complicated with more neurons because obviously you might have one neuron telling a neuron in the previous layer that it needs to shift one direction, while another neuron would like to see that same neuron shift a different direction. And then the cost function just averages, okay, what's going to be the most effective way to do this? And so it's like a compromising function for how to make the best adjustments to the cost function that improve accuracy. We'll skip the recap. And if you have any questions, you're welcome to email me. Anyway, ta-da, that's it.
Any quick questions, anybody? Any quick questions? Okay, thank you. Let's give them an applause.
Good job, guys.
And I do want to get to the next group because I know you have something really important to hour.
Yeah, really quick, can I just ask if everyone's cool with it, please let Larry record this because I've got to go back to work, but I'd like to watch these later on YouTube. Anyway, thanks.
Okay, thank you very much. And Eduardo and Cesar, are you okay with recording it?
I think we'll pass on the recording.
Okay, so you're going to pass on recording. So I'm going to pause. Hopefully this will work. Pause sometimes works. Okay. Victor, Ralph, it's all yours.
All right. My name is Ralph. And my partner is Victor. And we're going to do image compression and how it relates to linear algebra and some real world applications. So what is linear image compression? Well, image compression is a type of data compression applied to images to reduce their cost of storage or transmission. There are 2 types of image compression, loosey and loose-less compression. Loosey compression loses some information on the process of reducing the image size, and while loose-less compression doesn't lose any data, meaning that the original image can be reconstructed from the compressed one. One example of loosey is a JPEG that will go more in depth, and one example of lossless is a PNG that will go more in depth in later slides. And the picture that you are seeing right now is a JPEG, also known as Joint Photographic Expert Group, and it's the most commonly used method of loosey compression.
So how, because this compression involves using a computer, how a computer can look at an image. So here we're gonna use just gray images because we don't want to complicate the explanation by adding some colors. You can see on the left our original 520 by 520 pixel image. And we are gonna focus our attention for the next slide on the 20 by 20 section. Each pixel takes 1 byte to store, and you can imagine using some calculations that 520 by 520 pixel image like this one takes 0.26 megabytes to store. And if we add some color to it, it will take around 1 megabyte to store. So here is that 20 by 20 section that we zoom in the last slide. And this is what a computer sees. Each cell represents 1 pixel, and the number from 0 to 255 represent the brightness of each pixel. So what we can imagine that for the original image, we will have a 520 by 520 matrix. And because our knowledge of linear algebra, we can quickly realize that in the original image, we are working in R520 space. And this is our main problem. Now imagine if this was a color image, we will need 3 times the amount of information. And that is a lot for an image that is not an HD image.
While analyzing the original image, we could note that the table barely changes in the grayscale, as well as the napkin and some other objects. However, at the intersection of those sections is where we need to focus our attention, because things are drastically changing over there. That is what gives us the opportunity to compress the image using JPEG. It it doesn't make sense to represent the table or the napkin pixel by pixel, because there exists the case in which all grayscales are the same or at least very similar to tell the difference.
Okay, so now let's go to the linear algebra part. The information that Rolf just gave us about the original image is the key for image compression. The standard basis, which gives the value of each pixel, doesn't account that we have pixels whose neighbors tend to have the same grade level, as noted before, like the table or the napkin in the picture. What can we do to reduce the amount of information? Well, we can perform a change of basis. We have to think of a basis that addresses the fact that as humans, we don't perceive small changes in brightness. So let's try to imagine what are good vectors or bases. One vector that will fit perfect in our basis is the vector of all ones. This vector will give us all the information to represent a solid grayscale in our image, or like a solid color. And that is a great advance. We can also include a vector with half positive ones and half negative ones. These vectors will represent a spot that is half dark and half lighter. Now we can understand the point of changing the basis. Our standard basis is not the most optimized for our goal. And looking at our original basis, which contains 520 vectors, we can see that just the first vector of the new basis will take care of adding all the 520 vectors. And we can see that that saves a lot of work. So what is the best basis? And as I said, how can we change the basis? We now have the tools to change a basis. We can use a transformation. In this case, a linear transformation. The most common transformation used for JPEG are the discrete Fourier transformation, also known as FFT, and the discrete cosine transformation, or DCT. The difference between them is that DCT uses only real numbers, while FFT can use complex numbers. We are not going to look at how these transformations look like, but the idea is that they transform our basis to a better one. Now, how this works. So the JPEG transform compression starts by breaking the image into 8 by 8 groups. And why we use 8 by 8 pixel groups instead of, let's say, 16 by 16? The only reason is that at the time that they developed these standards, the maximum size that integrated circuit technology could handle was 8 by 8. And the 8 by 8 pixel size works well, and it may or may not be changed in the future. Within each group, we have 64 coefficients, 8 basis vectors, 64 pixels. We can change the basis in 64-dimensional space using the Fourier vectors. And this is a lossless step. We can put a vector x, and then we change the basis, and the vector gets translated to a better basis. So 64 pixels come in and 64 pixels come out. Now the compression part is in this new basis, we can throw away large coefficients because that means that the brightness is not changing too much. And removing 50% of the bytes from the high frequency components might remove only 5% of the encoded information. So we are removing a lot of bytes from the image, but we are not removing a lot of information. So looking at the compressed image, we can't see much of a difference. So here is an example of how the compression looked like. We can see on the top left corner the original image. And to the top right corner, we can see a compression of 10 by 1. That means that for every 10 pixels, we are only displaying the information of 1. And it is amazing that using just 1 pixel information, we can still display an image of the face. This saves a lot of information in the hard drive. And we can see that the difference in quality, although it's big, because this is a big compression, we can still see some details like the eyes, but we can see some parts of the face like the forehead that we can tell the difference there. Now we can see on the bottom right a compression of 45 to 1. That means that we are using just the information of 1 pixel to display 45 of them. And now we can see a big change of difference in the quality. Although it is surprising that we can still see the difference and tell that this is a face. We can see the eyes, that they still looking good. And on the forehead, we see the big difference. We see section of solid colors, but we can see that this saves a lot of storage without losing too many details.
So for a PNG, also known as a portable network graphics, is one of the most, if not the most popular lossless compression out there. Well, how it works? Well, first the computer takes the image, then converts the image into a basis, which the computer then finds the eigenvectors of the basis, which will later form an eigenvector basis to compress the image. The size of the image also gets reduced by changing of the basis. Afterwards, when a person wants the image back, it then converts the eigenvector basis back to the original standard basis. This transformation is also supposed to be one of the most efficient bases out there. However, just due to how complex it is and how many eigenvectors you might get, it might take too much computing power for some computers to handle and will make the file size extremely too large. And right here is a sample PNG picture of Mimikyu, where you can see how very high quality it is and how also transparent it is. Now there is extreme differences between the formats. while JPEG, its average size is 11.8 kilobytes, the PNG's average size is 4.4 kilobytes. However, don't get this confused, mainly because the only reason PNG has a lower average size is mainly because it's often used as computer graphics or icons, such as the YouTube logo, the Twitter logo, and maybe the Lake Tahoe Community College logo. But I think so it might use a different type of lossless um, format, while JPEG is often used in photography. Like the example before, PNG also supports transparency, while JPEG will not support transparency and will give and create a background image, despite it not having a background to begin with. Another difference is that JPEG is, even though it's mostly commonly used as a loosely compression, it can be used. There's a lossless compression out there, but it's not as popular compared to its loosely compression base, while PNG is only a lossless compression. Another fun history fact is that JPEG is actually a patent project object to this day. If you want to know it, the Princeton Digital Image Corporation owns the patent of JPEG, and the group who created JPEG is also the name of the JPEG, which is the Joint Photographics Experts Group. While PNG was created mainly because GIF, since GIF was a patent product by the Unisys Corporation, the tons of teams of people just wanted a free open source lossless compression, so they created the PNG just to spite Unisys in reality. Another final example is that PNG only has one file extension, while JPEG has numerous file extension as listed below. As such, these are some of the sample pictures. The top uppermost picture is actually a JPEG picture comparing the two picture of the same pictures. As you can tell, the JPEG is only 6.3 kilobytes, while the PNG is 377 kilobytes, which is way more than the JPEG. However, you could tell there's barely any loss of quality, and it's one of the more reasons why photographers love JPEGs, just because they could get that very small file size. As such, though, not all JPEGs are alike, and some have very low quality, such as this Roger the Fat Penguin one is kind of low quality, and this cat wearing this frog outfit is extremely low quality compared to the PNGs of the Twitter logo and the YouTube logo. Though it's kind of hard to tell since this is also getting compressed through the PowerPoint and is also getting compressed through the Zoom meeting as well. But another example is that, like transparency, as I suppose, you could tell that this dice is very high quality, and not only that, it doesn't have a background. Such with the same thing could be applied as the fire. Though there are some high quality image of a JPEG, like Vector wearing his suit and this I am completely insane doggo. Then again, it's kind of hard to tell that quality because of the ultra compression that we get from the Zoom meeting. Oddly enough, video compression actually works the same way as image compression. However, for this to work, the computer makes a picture of every single frame or second of the video, and then not only look at the color difference, but also the movement difference in the video. The computer compares the similarities and different types of movements and color of each pictures in relation to each other, and delete extremely similar movements and colors, and then the computer then predicts the movement and then recreates it by connecting the non-deleted movements together. Later, the computer then codes and digitizes the correction and then compresses the correction only. Hence the jumpy motion of mainly many extremely compressed videos. Not only that, most video compression uses the discrete cosine transformation basis, or at least a form of it, as stated from before, from like slide 8 and stuff. And usually one would use a lossless video compression to edit, so they don't have any loss of quality of video. Then they later use a loosely compression when the video is completed, so their video won't be like 500 gigabytes in space. One example of lossless video compression is the QuickTime Mov, which is an Apple product. And one example of loosely video compression is H.264, which is the standard of both Blu-ray, YouTube, Hulu, and Netflix. Basically the standard of videos in the internet. And this is an example of if you compress a video way too much.
To the milestone videos so you can check them out for yourself. All right, so I'm sitting in a room different from the one you are in right now, and I'm recording both the sound and an image of myself. And I'm going to upload it to YouTube, rip it from YouTube, download and upload again and again and again until all the original characteristics of my voice and my image are destroyed.
Okay, that's it. You're muted, Larry.
Are there any questions?
So that video was him re-uploading the video over and over again?
Yeah, 1,000 times to see how the YouTube compression affect the video.
Oh, okay.
Any other questions?
Is it possible for the transparency layer of a PNG image to be altered by compression?
I think so. There's some like the lossless compression. There's actually two forms of it, which also has its own problems. I don't know which one is the worser one, but the two versions has their own problems. So maybe one of them is related to your question, Jacob.
All right, thanks.
Any more questions?
I think just one comment I want to make is that we can see on the PNG they use the vectors, eigenvectors basis, and this is another example of why that is a great basis to have, because basically that gives us all the information of a matrix, so we can reconstruct them from the eigenvector basis.
Great. Hey, anything else? Okay, thanks everybody. I want to mention a few things. One is I'll grade these definitely by tomorrow, maybe today, but I'll definitely grade them. I don't take my time. You know how I am about grading. And Friday is the final. Take it seriously. It's a big part of your grade. I will have office hours today, like in 3 minutes. And then also I'll have office hours tomorrow. I'll have office hours on Thursday. There's no need on Friday because your final's over. Class is over. But definitely, you know, this week I'd be happy to answer any questions you have. You can also email me and I'll help you with any problems you're working on. You know, if you're working on the practice test or you're working on other problems from the book or whatever it might be, or my handout. And I'm definitely happy to help you out because again, I want everyone to do well and hopefully it goes real well. And you know, you're used to it now, so you know how the test is going to be. Make sure you have a camera so you can take a picture of the of your test and upload it when you're done, because that's sometimes a pain. And make sure you know it's readable. That's always important too. Any questions about anything? Because this is the last time actually. We don't have another Zoom meeting. This is it. Unfortunately, we're not. I didn't get anything back from the dean, so we're not able to have a review session Wednesday. So that's why I did Friday, last Friday. But any questions about anything?
The finals at 12 on Friday, yes?
Yeah, finals at 12. Again, I'm going by what it says in the schedule. So I try to, you know, stick with the rules because that's what you signed up for, whether you like it or not, but it was in what you signed up for. So 12 o'clock is when the final is. It will open then, and then it closes at 2. And then I'll have it graded by the end of Saturday for sure. It does take time to grade. But you may, I don't know if you'll be able to see it because the class is over Friday. But you'll definitely be able to see your course grades next week. Because that's
There's office hours Wednesday, right?
Yes. There's office hours Wednesday. There's office hours today. Office hours Tuesday. Office hours Thursday. So I do have office hours, you know, and no reason Friday. So I doubt I'll have office hours because it's over.
Yeah.
Yeah. Any other questions? Okay, I think I'm going to stop the recording. Hopefully it worked. Whenever I pause and start again, sometimes it doesn't. We'll find out.